Hello and welcome back to Let's Code Physics. We are in episode 3 in our series on subscriber tribute, where every country that we have subscribers in is represented by a bouncy ball inside of a box. We've successfully set up our code where each country is represented by a bouncy ball that follows a trajectory where it will bounce off of each wall of the box, but we haven't yet put in an interaction between the bouncy balls, so they're just sort of passing right through each other right now. So our goal for today is to set up the math that we need in order to model that collision, and then in the next episode we'll be implementing that math into the code itself. This is actually the second attempt at recording this episode. I got into this episode and the next one. I actually got it programmed in and then discovered I had a pretty serious math error. And we are moving extremely slowly. Okay, I found my problem. Still frozen. I'm thankful to this print statement for helping me see that. And we should get it going now. Okay, yay! Oh, warning! Math domain error. What happened here? This just in. The error is in this 2 minus 2 mu minus mu squared factor, which apparently has turned out to be negative. Oh, this might be where I went wrong. Okay, I think I did a little too much at once here. A, B, and C. So x is equal to negative b plus 2m. I am buried in paper at this point. Someone help me. This was supposed to be, I think I wrote a mu2 instead of a mu. And that seems to have been the problem, because then I ended up with a mu squared instead of a mu to the fourth. Found another mistake. I missed a double negative being a positive. And so hopefully things will go better today. So I'm sort of caving today. We'll be using, rather than me doing the math, we'll be using Wolfram Alpha, wonderful reference online. So the way the model needs to be set up is that we've got two bouncy balls that'll be colliding with each other. So presumably these can have different masses. So one will have a mass 1, one will have a mass 2, and they come in on some, let's draw that a little bit different. They come in on some collision course with each other. So the idea is that we give each one an initial velocity, call it v1 and v2, and then afterwards, so after the collision, they will rebound off from each other in different directions with different velocities than they had coming in. And so they'll have the same masses, obviously, but they'll have a different velocity than they had before. So we'll call those new velocities v1 prime and v2 prime. So the prime just indicates that it's different, that it's new, that it's changed from the way it was before. What we're going to do is we're going to use a few different physics principles in this. The first physics principle we're going to use is something that you can apply to any collision, and that's conservation of linear momentum. The idea of conservation of linear momentum is that the movingness of the object doesn't change from before the collision to after the collision. So what that means is that the momentum of the first bouncy ball, that's just its mass times its velocity, plus the momentum of the second bouncy ball, that's its mass times its velocity, before the collision, so this is without the primes, has to equal the total momentum at the end. So the same equation, but this time with primes. So if you think of that in terms of the two, oops, that should be a 2. So if you think of that in terms of the two pictures that are above, what this means is that the total momentum in this picture should be the same as the total momentum in this picture. And that's a universal principle that's going to apply in any collision that happens. And since we're dealing with 2 dimensions here, we've got to be thinking about the different components of the velocity vectors. And since we're dealing with 2 dimensions for right now, that means this equation is actually really 2 equations, one for the x and one for the y, or as we'll see in a minute, we can rotate those axes to make them a little bit more convenient. But unfortunately, that means we've got 4 unknowns. That's 2 velocity components for v1 prime and 2 velocity components for v2 prime. But we've only got the 2 equations with 4 unknowns. So this is where we're going to make another assumption. So this thing, conservation of linear momentum, is always true. We're going to make an assumption on top of that, that this is what we call an elastic collision. The idea of an elastic collision is that there's no energy lost to the surroundings. There's no sound made, there's no heat dissipated, there's no deformation to the bouncy balls. Let's hope there's not any deformation either. But what that means is that we've also got a conservation of kinetic energy. I can write a better K than that. There we go. The idea behind kinetic energy is that it's similar to momentum. It's equal to 1/2 mv squared. It's a scalar quantity, not a vector quantity. But if we're not losing any energy, then that total amount of kinetic energy before should also be the total amount of kinetic energy after. So I can write a similar equation, and I'm actually going to just ignore the 1/2 because I can multiply everything by 2 and the equation's the same. But just please know that, yes, I know that kinetic energy is 1/2 mv squared. So we've got an m1v1 squared plus an m2v2 squared has to equal the same thing but with primes. m1v1 prime squared plus m2v2 prime squared. Cool. So you notice I'm not putting vector arrows over these things because when you square the velocity, you're actually taking the magnitude of the vector and squaring it. So that gives me 3 equations, but I've still got 4 unknowns, and this is where we've got to make one more assumption. So what I'm going to do is go back up here to the diagram, and we're going to introduce an assumption here. It's actually a pretty valid assumption. We're going to assume that when these two bouncy balls interact, that the force they exert on each other is only directed along the line that goes between the two centers. So in other words, if one bouncy ball is coming in at this angle, the other one's coming in at this angle, when they connect, the only force they can exert on each other is a force that points from one center to the other. There can't be any force pointing perpendicular to that. So I can think of this thing as being like a parallel axis. Let me label that in black. There we go. So I can think of this thing as being like a parallel axis, and I can think of another axis as being perpendicular to that. Oh, I managed to get that pretty good there. All right. Of course, I had practice. I had the disaster video from earlier. So I could think of this thing, instead of thinking in terms of x and y, which we just set up because we're used to thinking in terms of up and down and left and right, I can rotate those axes to talk about the direction that's parallel to the center-to-center line and perpendicular to the center-to-center line. In order to do that, what I have to do is I have to think about a new vector. I've got to think about a vector r hat as being the two positions of the bouncy ball. So think of that as r2 minus r1 divided by the magnitude of that r2 minus r1. So the reason this vector gets a hat is because it's what we call a unit vector. A unit vector is defined such that it has a magnitude of 1, so I can do all sorts of neat stuff with it. Particularly what I'm interested in doing is I'm interested in breaking up the velocities into not their x and y components anymore, but their parallel and perpendicular components. So I can take any of the velocities, and if I dot it with the r hat, a dot product just means you're taking one vector and another vector, and you're taking the first vector's projection along the second vector. It's an operation that our code knows how to do, that the programming language knows how to do. And that will give me the velocity in the parallel direction. So that'll give me the velocity component that is parallel to the center-to-center distance. Now, as long as I'm just taking a dot product, this thing has to be a scalar. It can't be a vector. So if I want this thing to be a vector, I just multiply by r hat. So think of it like you're taking this vector, this velocity vector, collapsing it down into a scalar value, and then you're shooting it along the r hat direction here. Then if I want the perpendicular vector, all I have to do is take the original vector, the total vector, and subtract the v parallel that I just calculated, right? Because whatever's left over must be in the perpendicular direction. And so what we're assuming is that the force is only acting in the parallel direction. What that means is that I can only change the momentum, or I can only change the velocities in that parallel direction. I can't change the velocities in the perpendicular direction. Another way of thinking about it is, if you think about this as like a rock skipping across a lake, the bounce is going to change the rock's vertical velocity, but it's not going to significantly change the rock's horizontal velocity. So what that means is that the velocities in the perpendicular direction cannot change. So what that means is that if I take v1's perpendicular velocity in the initial state, that's got to equal v1's perpendicular velocity in the aftermath, in the after state. If I take, I need a vector there, and I can do the same thing with v2, that its perpendicular component is equal to its final perpendicular component. So the two perpendicular components don't change. So you remember earlier I mentioned that these two, that this conservation of linear momentum equation is going to give us two equations. Well, it'll give us one in the parallel direction and one in the perpendicular direction. So I can break up that equation, and I can say that this means that m1 v1 parallel, so this is a 1 and this is a parallel, plus m2 v2 parallel is going to equal m1 v1 parallel prime plus m2 v2 parallel prime. So all I've done is taken the conservation of linear momentum equation and added parallels to everything. It also means I can do the same thing with the perpendicular components. So here I'm just going to change out all of the parallel signs for perpendicular signs. M1, not M7, there we go, M1 V1 perp prime plus M2 V2 perpendicular prime. Now here's the thing, having V1 perpendicular equal to V1 perpendicular prime and V2 perpendicular equal to V2 perpendicular prime automatically satisfies this equation. So this equation is automatically taken care of. I don't have to worry about that one. The only one I do have to worry about now, well, one of the ones I have to worry about now is this equation right here, the parallel equation. So I'm going to call that equation 1. And then I've also got to satisfy the conservation of kinetic energy. And now that I've got my components, I can rewrite these magnitudes in terms of components. So that's going to become an m1 v1 parallel squared plus v2, plus v1 perpendicular squared. So think of this as like the Pythagorean theorem, like x squared plus y squared equals the hypotenuse squared, only now instead of x and y, it's parallel and perpendicular. It's still a right triangle, it still works. Plus the same thing for 2, m2 v2 parallel squared plus v2 perpendicular squared. Has to equal the same thing with the primes. So this has to equal m1 v1 parallel prime squared plus v1 perpendicular prime squared, have to fit in the prime there somewhere, plus m2, open paren, v2 parallel prime squared plus v2 perpendicular prime squared. All right, everybody has parallel and a prime, parallel perpendicular, parallel perpendicular, parallel perpendicular, parallel perpendicular, parallel perpendicular. Okay, we're all good here. But since I've got these perpendicular components equal to each other, what that means is that the v1 perpendicular squared here is going to cancel out with the v1 perpendicular prime squared there, and the v2 perpendicular squared here is going to cancel out with the v2 perpendicular prime squared there. So all I have left is this equation with the v parallels. I'm going to label that one equation 2. Now here's the fun part. I now have two equations and two unknowns. The only unknowns I have are the v1 parallel prime and the v2 parallel prime. Only unknowns I have are the v1 parallel prime and the v2 parallel prime. And this is where I'm not going to make the same mistake as last time. This is where I'm going to go to a trusty site, wolframalpha.com. Wolfram Alpha is very popular among my students. It's basically it's a super online graphing calculator. It's where you go when you've spent pages and pages on mistaken algebra, and you plug in the thing that you wanted to solve, and you say, please solve this thing for me. The perspective I have on Wolfram Alpha is the scene on The Dark Knight, where they're on the ship full of the criminals that are being taken out of Gotham City so that they can be sure that they face trial. And there's the scenario where the Joker says, one of you is going to blow up the other one, and the big hardened criminal says to the security guard, give it to me, and I'll do what you should have did 20 minutes ago. I feel like Wolfram Alpha is that guy. It's always beckoning to me, give it to me, and I'll do what you should have done 20 minutes ago. Anyway, how my brain works, connecting movies with math. Anyway, so what I'm going to do is I'm going to do a little bit of algebra here to take equation 1 and isolate v2 parallel primed. So what we're going to do here is we're going to copy this side over. So I've got an m1 v1 parallel plus an M2 V2 parallel. And if I want V2 parallel prime by itself, I need to subtract over the M1 V1 parallel prime. And then I've got to say that that equals V2 parallel prime, but I've got to divide both sides by the M2. So this thing's going to get divided by M2, this thing's going to get divided by M2, and this M2 is just going to cancel out, so it's going to go away. So I'll have my V2 parallel primed equals this thing. So where I have the V2 parallel primed in this equation, I'm going to plug in that. So here's the game plan. I'm going to take this equation 2 and I'm going to plug it into Wolfram Alpha and ask it to solve for me this unknown V1 parallel prime. Now, all the parallels and the primes and everything potentially going to get confusing, so we're just going to call these V1, V2, and X. That's all we're going to do. Okay, so we're going to say that I want this thing to solve M1 times V1 plus M2 times V2. I think that's what I have over here. Oh, excuse me, I've already forgotten the square. There we go. Forgot which equation I was on. So M1 V1 squared plus M2 V2 squared. All right, I've got an M1 V1 squared and then nothing plus an M2 V2 squared and then nothing equals an M1 times the unknown thing squared. All right, this is M1 times the unknown thing squared plus M2 times something. And this is where I'm going to plug in this thing that I solved for V2 parallel prime, so that I've only got one unknown in this equation. So I've got an M1 divided by M2 times V1 plus, here I've got a V2 minus, I've got an M1 over M2 times, this is now the unknown thing, so this is X. So I've got an M1 divided by M2 times X. And that whole thing needs to be squared because I'm plugging this V2 parallel prime, I'm plugging this 3-term thing into this V2 parallel prime here. So I've got that thing squared. All right, let's double check our equation here. So I've got M1 V1 squared plus M2 V2 squared for the left-hand side. M1 V1 squared plus M2 V2 squared. Cool. And on the right-hand side, I've got M1, the unknown squared, plus M2 times this thing. M1 unknown squared plus M2 times the thing squared. And the thing squared should be M1 over M2 V1 parallel plus V2 parallel minus M1 over M2 V1 parallel prime plus times the unknown. So I've got M1 over M2 V1 plus V2 minus M1 over M2 times X quantity squared. Okay, great. So I've got my equation translated over to Wolfram Alpha. I'm asking this thing to solve for X. So I say solve, give it the equation, comma X, and here we go. And this thing is going to do its little computer animation thing. Oh, it doesn't even bother with the animation. It says that was an easy problem. So there's two possible results, right? This is a quadratic equation, so there's always two possible answers. The first possibility is that the unknown, so remember X is V1 parallel primed, is just V1 parallel original. So it's entirely possible, it is physically possible, according to the equations, for mass 1 to continue on with the same velocity that it had before. What that means is that that M2 would continue on with the same velocity it had before. Basically what that means is the two things pass through each other. Physically, we know that's not what happens, so we don't choose that solution. The equations say it can happen, but we know it's not going to happen. So what we do is we pick the second one, that the unknown is going to equal this combination, and I'm just going to copy that over to here. And so what I'm going to do is I'm going to put in a little green squiggly line to say that this is where Wolfram Alpha happened. WA, there we go. Because I'll have this canvas available for you as an image file in the description below. So just to remind you, this is where we did the Wolfram Alpha step. So what I get is that the unknown is M1 V1. So I get my black marker back here. So V1 parallel prime is equal to M1 V1 parallel. Remember, I just dropped the parallels because those are the only things left. Minus M2 V1 minus M2 V1 parallel plus 2M2 V2 plus 2M2 V2 parallel, and that is all being divided by M1 plus M2, right? This thing is a velocity, so the masses, I need a mass in the denominator to cancel out the masses in the numerator. So I take all of this divided by M1 plus M2. All right, let me just double check this. I've got an M1 V1 minus M2 V1 plus 2M2 V2. M1 V1 minus M2 V1 plus 2M2 V2, all over the total mass. All over the total mass. Wonderful. Okay, cool. So that is a lot simpler than the thing that was giving me a square root of a negative number the last time I tried this. So this is a big success. So what we are going to do in the next episode is we're going to take this outcome for the collision along with this outcome, because we don't want to forget that we also need to update mass 2's velocity, and we're going to plug those in so that our bouncy balls can be bouncing off of each other and not just the walls. So thanks so much for watching. See you next time. Bye-bye.